Another direct method is what we call LU decomposition. So it is possible to show that any square matrix A can be expressed as a product of a lower triangular L and an upper triangular matrix U. So from this simultaneous equation AX equals B, A can be replaced by LU. So then we have this expression LUX equals B, where UX is equal to Y. We have then, given this expression, we have Ly equals B. And which can be solved for y for forward substitution. Then solve for x in the equation ux is equal to y using back substitution. And this will yield x by the back substitution process. Actually, it's almost close to gradient method, or Gaussian method. Okay, for example, the Doolittle's composition is very close to Gaussian. Okay. Now there are advantages, no, for LU decomposition. First, that A can be decomposed so that we can solve AX is equal to B for as many constant vectors B as we please. So, for example, we have a system. Say, imagine a robot, and then given with different B, different condition in time. So A can be decomposed into LU, and then we can solve for X immediately without doing the, for example, Gaussian method. We're just multiplying vectors so and so, very easy and faster. So for this application, when we have different or many constant vectors B, and LU decomposition is better compared to Gauss elimination. Okay? Now, let's try an example among the three most common types of LU decomposition. We have Doolittle's decomposition. So Doolittle decomposition is simply we have a lower triangular matrix L and then the upper triangular matrix U with the following values. If you can remember in Gaussian, we have actually solved L21 in Gaussian, L31 and L32. So this is during the forward substitution method, where L21 is the factor multiplied to the first equation and the Gaussian. So if you let's look at Gaussian in this case. You can remember here, we multiplied 4 with a value such that it will be equal to -2. So what did we how to multiply that one? We get 4 divided by -2. -2 divided by 4. So that's the constant. No? That's -0.5. So basically, -0.5 is the L. Okay? L21. And then multiply in 1. So that's 0.25. 0.25 is L31. And then in this case here, so -0.5 multiplied to -2. Okay, so -0.5 times, 3. -0.5 times 3, that will be -1.5. So they're the same. So that will be the L32. Okay, so we have three values, and that's L21, L31, and L32. Okay, and then the following U here, these are the values we multiply during the backward substitution. Okay, so this one, for example, we have, in this case, we have, if I'm not mistaken, this one is the 9/3. So this is 3. Actually, I have to go back. Where's that? Sorry. Here, U33 is the value same as the matrix, or identical to the derived matrix here. So you have here 3, -1.5, 3, 1, -2, 4. Basically, this is the U in the LU decomposition. So first the L are the multipliers or the constants, and then we have the U. Okay, so that's the Doolittle decomposition. So to verify whether multiplying LU is equal to A, so if you multiply L and U, so this is the product. And then applying Gauss elimination to A, so such that the same process as the Gaussian elimination, so and so, and then we find that LU, okay, so A double prime is equal to U11, U12, so which is the same. Okay, so we were able to derive the U here if we multiply L and U to the U itself. Okay, so therefore the final coefficient matrix is we have this L U. So this is an expression, no, for the LU decomposition. So you can combine L and U. Okay, so we call this one the form, no, the form of the LU. So similarity of the Doolittle algorithm. Let's try some example how to use LU. So we have here an example, okay, and solved AX is equal to B, a simultaneous equation. Now we have a manual solution here. So we have this expression, we have L and we have U, and then okay, so here we already decomposed. Okay, so here we used Gaussian the same code as Gaussian, or I mean the process of getting L and U. Okay, so you have L here 1, 2, negative 4.5. Then we have the other U derived using Gaussian elimination. Now having derived L and U, you can simply solve directly L and B first, okay, and then you will get the answer for your y1, y2, and y3. Okay, so that's the y1, y2, y3 as expressed in the LU, this process, no. So here, okay, so once you get y, and then uh, when you get y, then you can get the x. Okay, because uh, ux is equal to y, if I'm not mistaken here, ux is equal to y. Okay, so ly is equal to b, so therefore the expression here is simply y, sorry, so we have y is equal to ly equals b, so therefore y is equal to L negative 1b. Okay, so this was the first, and then we have to get x from the expression ux is equal to y, so we have x is equal to u inverse 1 y. So therefore we have y here, you can substitute actually, so you have u negative 1 and then L negative 1, then b. So basically this is how we solve the x. Okay, so going back to the equation, to the manual solution, so we have here, okay, so getting y first and then we can get the x. The beauty of this method is that you can simply do a simple, simple iteration, or if we're using matrix form, you can simply multiply and then you will get y1, y2, y3 directly, and then you can solve it here, plugging in 7, 6, 18, then do the select the forward. I think this is the backward method. Okay, then you will get the x, x3, x2, x1. Okay, so that's for the manual process. So we were able to solve for x. Okay, take note the similarity of Gaussian. Okay, so the important thing for Doolittle is that the decomposition of L and U, and it will make us easier to solve for the x. Okay, so for Gaussian, it's just a straight way, no, this one is like a parallel way of solving. Okay, so So given the same values in the above equation, okay, oh sorry, I haven't run first this code. So import numpy as np, hopefully it will run. Okay, so I can remove this one. Okay, and then so this is the function. So if you notice, this is quite similar to Gaussian elimination method. Oh, sorry. Okay, so return A. So LU decomp. So A is decomposed. So the returning value is the L slash U. This one. Sorry, this one. This is the return value. So the LU decomp. So that code will return this value. Given this value here, 1 for 1, 1 to negative 2, and it will result to this. So let's verify. So we can actually verify that one. Okay, so we have run the function, user defined function here, and we can actually try running the decomp A. Okay, we can run that one, and let's see. Oh, sorry, we haven't defined A, so actually this should be capital A. Sorry, I'm using capital A. Okay, so if you see 1, 2, negative 2, 4.5, so which is the same as here. Okay, so that's the first step. So we were able to decompose the A, and then we can solve for the value of x. Actually, this is the same as the one in Gaussian, but with a new thing. Okay, the new thing here is that we separate the y and the x. So for Gaussian, if you can remember, for Gaussian, it is direct. I mean, all the steps. Okay, here. Okay, from negative 1. So the backward substitution really a rigid. You see here the equation. This is really it consumes a lot of memory. Okay, and also the computation time may not be that fast. No, so here in the LU decomposition, so we follow this step. Okay, so for the Gaussian, so actually for the Gaussian it's very simple because we know AX is equal to B. Actually X is equal to A minus B. Okay, A inverse B. So this is for Gaussian, but this is quite time computing power demands power computing resources. So actually here we just simply get we have the L and U. Okay, so we have the L and U, and we can solve the A and B. So actually the A here should be okay. So we will try to, this is it's like the backward substitution for Gaussian. So if you run this user defined function, and then you have this LU decomp. Okay, and this is the A from, it's supposed to be the A in the we can run this one. Okay, sorry, this is decomp. This is the same as this formula here. Okay, we can actually remove this one if you like. Okay, so having decomposed A, you know already how what's the it's the L slash U matrix, and then we input that one to the LU solve. Okay, so so you have the A. Oops, I think it's not the correct A. So let's run this one again. Okay, and then this one. Okay, be careful with that because here we're using the same local variable. So if you use a input here, so the values of the given value will be changed also with the decomp. So that's why in the second run, so it changed. So if you run this again, so you will notice it's a different value. So we need to make sure that actually we should have change the A here such that there will be no conflict. But yeah, so that's a bug, and you can modify that one later. So having solved AP, so we can solve given the b in the ax equals b. So actually this is the step here. Okay, so here this one. Okay, so we can run this one, and okay, so the result is, oops, sorry, I think we should run this again and run again. So oops, do we have the same result? Oh, sorry, I think we have different b, 7, 13, and 5. Let me run this again, and then run this again, then run this again. Okay, so I think there's a mistake also in the other side, no? Because the A here is the previous one. Okay, so yeah, 5, 1, and negative 2, which is the same as 5, 1, negative 2. Okay, so yeah, we were able to solve, we were able to demonstrate to you the Doolittle decomposition method.